How we doing, class? Uncle Jegs here. Today we're going to be going through directing groups and disubstitution. You already know what to do. We've got the retrieval questions here. Answer them in full sentences, then we're going over the answer. Nitration of phenol makes 2-nitrophenol and 4-nitrophenol. Alkylation of benzene require haloalkanes, aluminium chloride, and you heat that under reflux. Bromine water decolorizes and a white precipitate is formed when you add bromine to phenol. These are the specification references that we're going to go through in today's lesson. Make sure you've highlighted them. So, disubstitution. Let's go through what this actually means. Di obviously means two, like dioxide, and substitution means replacement. Many aromatic compounds actually undergo a second substitution, disubstitution. So you don't just get one substituent added to your aromatic ring. Sometimes two is added. So we've got this activity here. I'm asking you to draw the reaction between phenylamine and bromine to make 2,4,6-tribromophenolamine. So we have our phenylamine, and I'm going to balance this already. So we've got 3 lots of bromine, and that reacts to make 2,4,6-tribromophenolamine. And obviously, because we've substituted that hydrogen that was on the aromatic ring, we're going to make hydrogen bromide, 3 moles of hydrogen bromide as well. And bromine actually reacts very rapidly with phenylamine. Keep that in mind. Now have a go at this activity. Draw the reaction between nitrobenzene and bromine to make 3-bromonitrobenzene. So we start with our nitrobenzene, and again we're going to add bromine, and that gives us 3-bromonitrobenzene. Again, we're substituting that hydrogen, and that's going to react with the other bromine atom to make hydrogen bromide. Unlike the phenylamine, nitrobenzene reacts slowly, and you need a halogen carrier as well, and high temperatures, and you can probably guess the halogen carrier should be aluminium bromide. That brings us to this actual lesson now. One of these actually activates substitution. It allows substitution to happen readily. Another one deactivates substitution. It's a bit more difficult to get substitution going on. Spend some time, think which one activates substitution and which one deactivates substitution. Of course, phenylamine reacted readily, so that activates. So NH2 activates substitution. And the nitrobenzene deactivated substitution because you needed a halogen carrier. You needed high temperatures. So NO2 deactivates substitution. But that's not all. One of them directs the second substitution to the 3rd position. Which one was that? The one that directed to the 3rd position was actually NO2, the nitro group. But the amine group directs the second substitution to either the 2nd position or the 4th position. This is why they're called directing groups, because it's almost like you've got a ticket that directs you to where your seat is meant to be, and your seat could either be in the 2nd, 3rd, or 4th position. Alright now, so I've got the 1 position being highlighted by this X group over here. And we've got positions 1, which is the X, position 2, position 3, and position 4. We have special names for these positions. And I've got the meaning of those names here. We've got para, which means against. We've got ortho, which means straight or upright. So you're standing upright. And we've got meta, which means after. Have a think and guess. What should we match up to the 2nd position, the 3rd position, and the 4th position based on the meaning of these names? If you overthought this, it could have been difficult, but the first one, which is position 2, should be awful because you're straight up, you're standing straight up next to that first position. Then if you use deductive reasoning, the third position would mean right after that straight up position, and then para, which was probably the easiest one, which means against, so you're moving against where that other X group is. So position 2 is awful, position 3 is meta, and position 4 is para. Awful, meta, para, OMP. Alright, so I have a substance here and I'd like you to have a go at these challenge questions, okay? We should name this compound 3-bromo-nitrobenzene. This is asking you, was the base compound activating or deactivating? And we've got a nitro group there. You should remember that's deactivating. This reaction was pretty difficult, so we needed a halogen carrier and we needed high temperature as well. Now it's asking you to give the full name based on ortho, meta, and para. What should we call this? It should be called meta-bromo-nitrobenzene or M-bromo-nitrobenzene. It's actually better to use the M rather than saying meta, okay? So instead of saying 3-bromo-nitrobenzene, we could just put M-bromo-nitrobenzene. That brings us to this activity now. I'd like you to give the IUPAC name and also the OMP name for these 3 different compounds. So the first one is 3-chlorophenol, and that 3 position, we can transmute that to M. If you look at 3, you can kind of twist it anti-clockwise and you see that becomes an M, so hopefully that helps you remember that. The next one is 2-bromo-methylbenzene, and that bromo group is standing upright, so that's O-bromo-methylbenzene. Now for this one, we have to put this in alphabetical order because one is in a 1 position, one's in a 4 position, but we just have to know which one's which. We've got a methyl group and we've got a nitro group. M comes before N, so it should be 4-methyl-nitrobenzene. And that 4 position, you can kind of think of it like a P. 4 is a P if you flip it the other way around. And that gives us P-methyl-nitrobenzene. When we're actually making organic compounds, that means that when we put the first substituent on our benzene ring, that substituent, depending on what it is, it can direct the position of the second substituent. And I've got this table here that tells you the different directing groups. The first column, we've got what are the 2, 4, the ortho and para directing groups. So if you put an amine group on your benzene ring to make phenylamine, and you try to substitute another substance onto it, another group onto it, that group is either going to go on the 2 position or the 4 position. I hope that makes sense. And so if you use a meta directing group, a 3 directing group, that means I start off with the benzene ring, I add a nitro group onto it, that's the 1 position. And then if I want to add another substituent onto it, it's going to go to the 3 position. So I'm going to have a 1-3 substance. What you also need to know is that all of the 2-4 directing groups are also activating groups, except for the halogens. That's why I've got a special color. They've got their own special group there. All of the 2-4 directing groups are activating groups, except for the halogens. So if you've already got a 2-4 directing group on your benzene ring, apart from a halogen, it will readily react. And all of the 3 directing groups are deactivating groups. So it kind of shuts the reaction down if you don't add extra heat, energy or catalyst or halogen carrier, etc. Now that we've got that there, of course, you know what's going on. I've got these challenge questions for you to have a go at. Do your thing. The challenge question is asking you, give the OMP name for the products formed through the nitration of benzoic acid. So we've got benzoic acid. Let's look for the group that is. The carboxylic group is a free directing group. So we're going to have a free directed substance. And it's a nitration, so that's free nitro benzoic acid. But it's asking us to give the OMP name. So that will be M-nitro benzoic acid. And if we draw that substance, we've got our carboxylic group on the 1 position. We'll just go to the meta position. That gives us M-nitrobenzoic acid. Alright, this next activity, I'll prefer you to work in pairs if you're revising in pairs. Obviously, if you're by yourself, you've got no choice unless you want to make an imaginary friend. It looks like a lot. Let me break this down. It's actually pretty simple. Methylbenzene reacts more readily than benzene with bromine. It forms approximately 67% of one monosubstituted, mono means one. It forms 67% of one monosubstituted product of methylbenzene and 33% of a second monosubstituted product. Draw the structures of both organic compounds and suggest which product is formed in the greatest percentage. This looks like a lot at the moment, but let me just break this down for you. We don't have a disubstituted product. We don't have a disubstituted product here. This is a monosubstituted product. That means that we've got methylbenzene and then another group, which is going to be the bromine. It forms isomers. There's one monosubstituted product that's 67% of what you form, and another monosubstituted product that is 33%. Have a think. What is going on here, okay? Use the table next to you to try and work this out. Alright, let's see if you're able to work that out. So we started off with methylbenzene. Let's look at which directing group that should be. When we've got an R group by itself, that's this over here. So it's actually a 2,4 directing group. So we start off with that, methylbenzene. Let's put the numbers here. We've got position 1, which is our methyl group, and then 2, 3, 4, 5, 6. Notice that position 2 and position 6 are equivalent. So when we form a product that's position 2 and position 6, they're absolutely equivalent. So we're going to have double that amount. But we're also, because it's 2,4 directing, we'll also have on the 4 position. So we have 2 lots of the second position and 1 lot of the 4th position. And if we add those numbers up, we'll see that we're going to have twice as much of the ortho. Remember, the O means it's upright, right next to that first position. And we have half the number of the para, which is against the first position. Alright, so the reason why directing groups is important in organic synthesis is because we want to create specific compounds, and using directing groups can help us place atoms or groups of atoms in specific locations around our arene. So for example, we start off with benzene and then we have this compound here. Have a go at these challenge questions, okay? This one might have been a little bit tricky. You don't usually get a compound like this. But first of all, we have to have it in alphabetical order. That's why the chloral comes first. So we have 1-chloral-4-nitrobenzene, or we could simply just put p-nitrochlorobenzene. And which substitution is needed for this? We're going to need, because it's not in the 3rd position, we're going to need 2,4 disubstitution. Let's look back at our table now. What must have been the first substituent to get this substance? So let's look at this. We could have started off with nitrobenzene, but that directs to the third position. If we started with chlorobenzene, it directs to the 2 or the 4 position. So the chlorobenzene should be the first thing made. The issue here is that we're going to get a mixture of the 2 and the 4 directed substituents. So what we need to do is actually distill the products so that we can isolate the correct compound that we want. And so that's the end of this lesson. It was pretty short, but a very important lesson. Make sure you're able to tick off both of these boxes. If not, rewind the video and have a go again, okay? I'll catch you guys next week with the next section of organic chemistry.